All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about PWM things in the ESP32. I am super excited about this because holy shit, I finally understand PWM calculations and how the clock signal fits into this calculation, how the clock signal is um, for lack of a better term, transformed. I don't know if I would call that transformation though. It's more like we are filtering the clock signal. So like you have the clock signal, which in our case right now at least is 80 megahertz because I haven't figured out how to select the RTC fast clock instead of just APB clock. The APB clock is at 80 megahertz, so that's 80 million ticks per second. The RTC fast clock would be, I think it was 8 megahertz. I don't remember, but it's much slower than APB clock. That being said, I haven't actually looked, to be honest, but I haven't found a way to select a different clock other than APB clock. So that's our main clock source, right? 80 million hertz, 80 megahertz, basically. So that is our clock source. That's our essentially base clock. That gets fed into a fractional divider, and based on the division factor, that fractional divider decides how many of those ticks are not. How do I say this? That fractional divider basically decides that, hey, every this number of ticks, we're going to allow one tick to pass through. That's what the fractional divider does. And in this way, we are in a way slowing down the frequency. We are not really slowing down the frequency. We are only allowing one tick to pass through every few ticks. So in that sense, we are slowing down the frequency. That one tick that gets passed through, that gets counted by the counter. And depending on what your resolution is, you're going to be affecting the depending on what your resolution is, you're going to be counting that many ticks in your counter to represent one period in what do you call it? Represent one period within your entire frequency. So that's within your PWM frequency, not your base clock frequency. Um, and yeah, that's what I've been kind of obsessing over for the past couple of days at this point. Give me a second. I feel like I need to adjust. I mean, it's not that big of a deal. It's just bothering me a little bit. Um, okay, maybe I can try something here. I mean, it's okay. It's okay. There's light. There's light. It's visible. That the right side of the breadboard, that's visible. So that's great. Dude, I've been doing so much more research on cyberdeck stuff, more specifically. And dude, as like it's I feel like more people need to get in on this, and more people need to learn what I've learned, as in the definition of a cyber deck. It's not necessarily a full blown, you know, um, computer. It's not necessarily meant to be. I mean, it can be a computer, but the idea is that it's a purpose built machine. It's a machine that's built for a specific purpose, and you are either repurposing already built devices, or you are building your own device, and you're essentially trying to stay away from buying like the mainstream devices, buying mainstream things like whatever uh, massive computers and tablets and stuff like that. So that's a bit of the rebellious side of it, the rebellion side of it. But like in general, the whole the spirit of cyberdex is basically just building purpose-built devices, um purpose-built computing devices. But like apparently it's not even computing. That's the important part there, that these devices can be built for a specific purpose. They are it's not it, you're not limited to just. And I feel like me discovering cyberdex through TikTok is what kind of established this misconception that cyberdecks are basically the only way you're building a cyberdeck is, or the only way that you can say that you're building a cyberdeck is if you have something like a um, what's that called? Single board computer. So a Raspberry Pi, and you have a full blown OS on it, and you have a display connected to it. You have input peripherals and stuff like that. Um, I feel like I got the misconception of what cyberdecks were because my introduction to cyberdecks was through these kinds of videos. And to be fair, the people that were doing that kind of stuff, a lot of times, how do I say this? A lot of times the videos that were being made and that were being kind of marketed towards an audience, they were being made and or marketed towards people who are not necessarily very tech savvy, people who are not very um, people who are not necessarily in the maker community, in the hacker space, people who are not very tech savvy with microcontrollers, for example. So for those kinds of people, buying a Raspberry Pi and then buying not a display module, but, well, for lack of a better term, display module. Buying a ready-made display, buying a ready-made single board computer, and then flashing the OS onto, an SD card and booting it up in this computer. That would have been much more simpler, and that's what a lot of people have gone for, rather than, you know, very, very custom hardware. And that doesn't make their creation any less valid as a cyber deck. It's just that I feel like seeing that a whole lot initially gave me the wrong idea of what a cyber deck is. So I'm glad that I did research on this, and now thanks to this, I have a lot of ideas for cyber decks. I'm going to be doing a whole lot of more research on this. I have actually been doing a lot more research. I've been looking into so like, okay, in terms of creating. So my idea for a quote unquote cyber deck is the old terminal style thing. So basically, I'll build a bunch of these devices that don't necessarily have a whole lot of a whole lot going on in terms of display, which is great because that keeps them low power, right? The device itself doesn't need to have a display. What I can do is I can create my own terminal, and or my own little terminal. What do you even call those kinds of devices? Hold on. Because I wait. Hey, so I'm getting into cyber decks a lot lately, and I'm gonna be building my own um ESP32 based cyber decks. My idea here is that uh, I'm I'm gonna build a bunch of different devices for various operations, and then I'll build. Hold on, there's this mic stand is okay. Yeah, And then I will build a terminal device separately. Let me put that in double quotes. A terminal device separately, separately that will have a display and input capabilities. Capabilities there. And dude, I'm curious about this one thing as well. How do I very quickly, like on NeoVim, for example, like if I what's the best way to show it here? Here, okay. So let me write the word believe wrong. So B, that's wrong, right? Yeah, that's wrong. I comes before E in believe. Um, However, it's not saying that it's wrong right now. I have to turn on spell check. Now it says that it's wrong, right? And with spell check on, I can I can do something like this, and then it'll suggest, the spelling suggestions, and I have my correct spelling right here. I'm looking for something similar on Firefox. The thing is, so I have the ability to right click. I have the ability to right click, but there isn't spelling suggestions, or there aren't any spelling suggestions. Let me open up settings real quick. I'm just gonna like just a quick detour. I need to check this because I've had situations where I've had to do this. Because I'm very much, within the terminal these days. So like I've been um um refining my workflow, and that's why I have like these little, luxuries, like, or little um efficiency boosters, these little these little, what am I supposed to call this, these little added bonuses, like spell check, for example. And so I've kind of forgotten how you do it on the GUI side. um hold on, spelling, I'm gonna check. Okay, download dictionaries, how to use spell checking. Right click a text field to turn spell check on or off to change the language. Not all fields support spell check. Okay. Perhaps I need to download a dictionary. I have no idea what that means here. Add-ons. Okay. You know what? I'm not gonna go too deep into that. Anyways, uh device separately that will have a display and input capabilities, and I will essentially um, quote unquote log in to these devices via the terminal to control them, and maybe even get data from them. I actually just got this idea about the data thing. Yeah, I could technically use them for data as well. I'll have to see how to go about doing that. But yeah, okay. And maybe even get data from them. Well, okay. It's a terminal. It's supposed to get data in terms of displaying, at least. I'm talking about like actually storing the data. So that'll be a bit of a different situation. If I'm trying to like separate the concerns here, there might be a different device for display purposes. There might be a different device for, you know, terminal purposes. Okay, to these devices via, Sorry, zoned out. Okay. Log into these devices via the terminal to give input and receive output. I'm I'm trying to think of a word to use to call this terminal device. Any suggestions? Who knows? Maybe from the cyberpunk literature, from the cyber deck kind of literature, there might be some word. Okay, this is a killer project, building a distributed ecosystem of ESP32 nodes rather than one bulky do-it-all brick is a very slick modular approach. Dude, I'm oh shit. Okay, we are dropping frames. Hold on. I need to do something to solve that problem before we disconnect. Okay, are we good now? I think we're good now. Hopefully. Right. So, I'm glad that I took the time to do research on cyberdecks because I doubt I would have had this idea. Somehow reading about cyberdecks and the whole culture surrounding cyberdecks, it started giving me these ideas for different ways of doing things. And this way that I've just thought about, it's actually a lot more efficient. Like, imagine this. Okay, imagine I have a bunch of different devices that I've built. Let's say I've made maybe a misting machine. Maybe I've made an LED controller to control like the lighting in my room. Maybe I've made. I said about the misting system, right? Let's say an atomizer. Let's not say misting because I haven't managed to set that one up yet. But let's say atomizer. So um humidifier, let's say I have a humidifier system. Let's say I also have an RGB LED system set up. Let's say I have something else that's monitoring um something plants related because I do a lot of gardening, and I want to kind of do like a thing where I grow a certain I grow a plant with like a bunch of sensors. So I'm very tightly monitoring. Well, not exactly tightly because there's only so much that I can do with the tech that I have. But like to the best of my abilities, I'm monitoring the conditions that the plant is growing up in. So that includes soil moisture levels, and the temperature outside, and the amount of light, and there's various other things. I wanna try setting up something like that. So let's say that's another system that I have, right? Um, what was I gonna say? Oh yeah. So imagine I can build all of these systems and I don't need to attach a display to any single one of them. All I need is a terminal. And of course, I'll also need a standard protocol that I'm going to use so that all of these systems can communicate to the terminal and send the terminal messages of various sorts. Why was I mentioning this? I was talking about like how thanks to oh yeah. So what I was saying is thanks to learning about cyberdecks, I got this idea. Well, to be fair, I also got this idea because of my past knowledge and my current knowledge also of like terminal based stuff. But then through learning about cyberdecks, all of a sudden this bridge between my Linux terminal side and the electrical engineering side. It's thanks to Cyberdex that I got this idea. And okay, so my point with like I was talking about all of these systems, right? As examples, all of these systems that I build, um, without some sort of terminal or any way to communicate outside, these these systems would need their own displays. And display modules, even if it's something small like an OLED display, a tiny OLED display, the display module is going to take it's going to take up a certain amount of power. However, if I don't have a display module and if the ESP32 just has to communicate with the terminal, then it's going to be the terminal that takes a lot of the power because I'll have multiple screens, or one or maybe two. I'll see how many screens. I'll have a screen attached to it, essentially. I'll have a bunch of other things attached as well. But the point is, I can build a bunch of these systems, which are not power hungry systems. These systems are going to do what they're supposed to do, and anytime I need data from them, I can just use my terminal and have the terminal read the data. So the only requirement there is that I need to have a terminal that can actually read this information. But the advantage is that none of those systems are going to be very power hungry systems. So I can make these very efficient low power systems, like truly low power systems, and have them do a bunch of very sophisticated things without them being power hungry. That is all thanks to Cyberdex, dude. And there's like so much more research that I have to do. Like, for example, I was studying about the ESP32. Sorry, ESP Now. Yeah, ESP Now. ESP Now is a protocol that allows ESP to ESP communication, so device to device communication. And something that really made this click for me was so I was doing this research through Gemini. Initially, I didn't fully understand what ESP Now was, and then I understood that, yeah, okay, this is a protocol for communication. And when I found out that this protocol apparently uses the 2.4 or 2.5, somewhere in between that range, gigahertz frequency. So it basically uses the ESP32's, it uses the same hardware that the Wi-Fi uses on the ESP32, except it's not using Wi-Fi. It's using that hardware, but it's not using Wi-Fi. And as I kept doing more research, I learned that ESP Now apparently operates on layer 2 of the OSI model. So for those of you who don't know, the OSI model is essentially a conceptual model that it helps you understand how the data is being used in various different ways throughout a communications system, how the data is being changed in different ways throughout a communication system. So like you'll have various layers. You'll have the physical layer, which is your actual, the hardware that's transmitting this data. Then you'll have like a I think it's called a data link layer. This is where you can start actually, um, framing your data, and then you have higher concepts as well. Like, well, to be fair, okay, I'm saying framing the data, but like even on the physical layer, there is a certain amount of framing that happens. But this is like one level above the physical layer. The data link layer is one layer above the physical layer. Then above that, you have a couple more layers as well, where stuff like IP gets introduced. On the data link layer, you have, because this is it's still very close to the hardware, you have the concept of MAC addresses, which is essentially the hardware's identity. You, I want to say you can't change this, but then it depends. It depends. I'm still doing research on that because there were certain devices I'd seen where you could change, but then here, what do you call it? Gemini is mentioning that it can't be changed, at least on the ESP32. But yeah, that's your hardware address. I have to do more research on that. And then above that, you have another level where the concept of IP addresses comes in. That can be changed, definitely. Above that, um, you have IP, and above IP, I think that's where your TCP and UDP protocols sit. And then above that you have other protocols, and then above that you have something else. I think one or two layers above, you like one or two layers above the TCP UDP layer is where you start to get HTTP. So you get into your like application layer and presentation layer and stuff like that. So you see what I'm saying? The OSI model, it helps you essentially visualize on a conceptual level how your data is being framed and transformed and seen or read or whatever you want to call it by these various layers, from starting from the top level, which is your software layer, your very high level software layer, going all the way down to the hardware layer, all the way down to like the physical layer before it like goes out through a wire or goes out, over the air or whatever. It's really interesting. Like doing research on this, it helped me a lot. I've actually been doing research on the OSI model on and off for like a couple of years. I haven't like gone too deep into it, mostly because as you're doing research on these things, you also have to do research on what exactly those layers allow you to do. And so that means you have to study the various like protocols, at least as an example, to get an idea of what's going on. So for me, that was when I was learning about socket programming, like bare bones sockets. And dude, learning about bare bones sockets definitely helped me a lot. Holy shit. Okay, okay. Going back to ESP now. So apparently ESP now operates on layer 2. I need to do more research. I just realized this. So far, I've been doing the research through Gemini, and I'm expecting Gemini to have up to date information about this, especially something like ESP Now, for which the documentation is like very widely available. I'm expecting Gemini to have the accurate information on this, but like I should still confirm it in case of Gemini could get something wrong here. Um, but yeah, uh, according to Gemini, the ESP Now protocol, it operates on layer 2. So because you don't have all of those extra layers, those extra added layers of complexity, that's why you are able to do this in an incredibly power efficient manner. This also means that it's very bare bones. So there are certain disadvantages, like you won't have like a constant retry kind of thing, constantly like, okay, there's a chance that messages could get missed or other issues could happen as well. So like because you're working on a very low level, there are certain things that you are going to have to handle yourself, which would otherwise have been handled automatically by the Wi-Fi protocol. But that's fine, considering that we are doing very simple low level devices here. ESP Now kind of fits in. And the great thing about this is that because a lot of the devices that I'm making are ESP32 based devices, so if I use ESP Now, I wouldn't have to use any of the other um, any other sort of radio equipment, because there were I have a couple of other RF modules, but they are mainly for the 443 megahertz. I can't remember if it's 443 or 433. Give me a second. Let me look that up. 443. I think it's 433. Yeah, my bad. It's 433 megahertz. So this is apparently a very standard how do I say this? This is the best way I've seen it described is that this is the frequency used by dumb devices. This is the frequency used by your regular, home appliances and cheap toys and other such things. This is a very it's a very commonly used consumer level frequency. So we could use that. Um, there's also another aspect of there's another kind of 433 megahertz communication that happens, that is it's long range, or I think it's low power long range, one of these two. It's LoRa, basically. It's called LoRa. So this um the method of creating this signal, and the communication is slightly different from your regular, actually very different from your regular 433 megahertz modules. And because of that, that enables very long range communication. Also, the way that the wave is being modulated, it makes it so this wave is able to travel through a lot more than your regular Wi-Fi waves can travel through. So there are various things that Wi-Fi would struggle with that LoRa waves would not struggle with. However, LoRa does have its own limitations. I think one of the limitations is speed and bandwidth, like the amount of data that you can send and how fast you can send that data. It's not nearly as fast and not nearly as much as what you can push out through Wi-Fi. However, you get the added advantage of it being long range. Holy shit! I've been yapping about ESP32 and CyberDex, and dude, I'm excited for this. I'm like super excited for this. I've been busy. I've been busy doing research on all of this stuff. Give me a second. Let me open up my chat on my phone. Okay, all right. So, let's get back to what we were learning, what we were studying. So, recently we discovered that in order for and my assumption here is that when once we configure, actually this is something I had to ask Gemini as well. Um, my assumption is that once we configure this the channel, the high speed channel, or even the low speed channel, once we have called the configure method on the channel, my assumption is that the channel starts outputting the pulse, the PWM signal immediately, and it just continues that the entire time. So what I'm wondering is there a way to like turn this off? Should we be turning it off? Does it like constantly consume power, or like what's going on there? Because I don't see options to turn this off. Also, I in the past I was wondering why we have these HW methods. So another thing. Um set duty. Set duty. In the past I was kind of confused about whether set duty takes a 0 to 100. What do you call it? What do you call it? Whether it takes a 0 to 100. um what am I trying to say here? I'm losing my words. Whether it takes a 0 to 100%. Oh yeah. So in terms of range, what is set duty taking? So because we know that duty cycle is it's um it's given in terms of percentage, right? When we are describing the duty cycle, we are describing it in terms of percentage. However, because this method set duty, it takes a U8, that's an unsigned byte. So I was wondering whether we are supposed to pass in a value between 0 and 100, or between 0 and 255, because I wasn't sure if they were internally stretching out 0 to 100 up to 0 to 255. So, like, were they representing 0 to 100 as 0 to 255 instead? Because I have actually seen situations like that. So, um, I wasn't, uh, sorry, I wasn't too sure. Um, then I looked at the code. Oh, what just happened? There. Then I looked at the code for this. Let's go up to definition. Okay. So this is our definition, and in the comments here, it mentions set duty percentage of the channel. And here's the interesting thing. Once its calculation is done, then it calls set duty hardware. So the set duty hardware is the actual value. That's not the percentage. When we are passing in a percentage, then set duty calculates the actual value for the duty. So the maximum number of ticks that the signal should stay on for. Set duty calculates that, and then it passes that to set duty HW, which is um, that should be somewhere here. Set duty hardware. Yeah. So this is what actually sets register values and stuff like that. Well, maybe I'm simplifying it. I'm saying register values, but there's probably more going on there. Also, there's a function here that I didn't notice until now. Start duty without fading. And now it makes sense that now that that we have a function called wait, I've already opened this, so I don't think I need to close this. I can just move the buffer here, and yeah, so now it makes sense that we have a start duty fade, and then there's a start duty without fade as well. Maybe I can call this. Is this available? Like I don't know, because function is part of this. Doesn't have to be public, does it? This is being defined here. So this is, we are implementing channel hardware or channel HW for channel. I'm not seeing like pub keyword here. I'm guessing that depends on the channel itself. I'll look into, yeah, I'll look into the, what do you call it? Oh, this is interesting, dude. This is the entire like mapping. And this is why when we pass in a certain number, so before I was wondering, how is it that we're able to pass in we're able to use the same number enum, because if we look here, actually, where was it? Here. So if we look here in ls channel, we are using channel.number.channel0, right? In hs channel, we're using the same channel.number. Number is the enum, and also channel 0. So I was wondering, like, how are we able to use this? But it turns out um, it's because of this. So depending on what channel we pass in into, I believe, either the configure or the new or init method. Where are we passing this in? We are passing this into channel. There's a channel method. Okay, I'll look into this later on. Wait, this returns a channel, doesn't it? Yeah, ledc dot channel, and this, yes, this returns a channel. This returns a channel. So depending on what depending on which channel we choose here, it then decides which specific channel it's supposed to use. Which here they're mentioning signal, so I'm assuming this maps to whatever specific channel outputs there are. Because we have, and I'm so glad that I opened up all of these things. If we look here, in here, we have these channels being mentioned. So you can see channel 0 to channel 7, and same thing is here. For here we are looking at the HS timer, not LS. If S so and so, then this, else this. Okay, yeah. So in this block, it's the high speed timer, the high speed channels, and in this block, it's the low speed channels. They also have something set up for in case if it's not an ESP32. So I'm guessing here they're handling like platform differences. Um, but yeah, yeah. Holy shit, dude. This is yo, we are we are getting somewhere now. We are getting somewhere. Um Now what else? What was the next thing I was looking into? I was talking about like set duty. I learned about how set duty takes a percentage. So the reason it's taking a byte is because all we need is a value between 0 and 100, and the lowest one that we can get here is an 8-bit value. So that's an unsigned byte. So what we are passing in here is the duty percentage. Whereas if we did HW, I think in HW, the value depends on the resolution that you have set. Because if I remember, um, in where is it? Uh, Dude, I love having this plugin. This is the aerial plugin. Because of this, I have symbols. But yeah, okay. In set, where's set duty? Up here. In set duty, um, it is checking for timer.duty. Timer is coming from, where's timer coming from? Maybe from self. Yeah, yeah. Timer is coming from self. So in here, this is our channel, right? We are defined. Oh, timer. There you go. So in our configure method, we are setting what the timer is. And in our timer, we are setting what the duty resolution is. So in channel, we can see um, when we pass in the percentage. What was I saying? Yeah, when we pass in the percentage, based on the percentage that we have passed and based on the duty resolution that we have mentioned, it then calculates what what the actual value is going to be. So you can see here it uses the the duty. The duty is the bits, right? So we then use that as an exponent, and that's why we are using this here. So 2 to the power whatever, let's say 2 to the power 16, sorry, 2 to the power, let's say 2 to the power 4 for the sake of simplicity, would, sorry, I forgot what 2 to the power 4 would be. That's basically a 4-bit number, so 16, right? That's, am I wrong about that? That's 16. 2 to the power 4 is 16 because 2 multiplied by 2, sorry, I don't know why I'm suddenly like blanking on this. 2 to the power 4 is 16. 2 is binary. In terms of bits, 4 bits means 16 yeah, okay, okay, yeah, sorry. Just I don't know what just happened there. 2 what was I saying? The little glitch that happened made me forget what I was talking about. 2 to the power 4, 16. We were talking about duty resolution. So the duty resolution, not max value, duty resolution is 4 bits. So then we do 2 to the power whatever the exponent is. Exponent is our duty, our timer duty here, and that gives us the maximum range. So let's say we've done 2 to the power 10, which would be 1024. Okay, let's go to our Python interpreter here and do this. So that's 1024. Okay, so what this is going to do, this is going to calculate our range, and then based on the range, it calculates the actual duty value. So um, because duty percentage is being passed in as a percentage, so we multiply the duty range by the percentage and then divide it by 100. So that is because we know our duty percentage. Let's say we are doing, so we're supposed to get 512 here, right? Or we could do 256 as well. That's fine. So let's say 25%. uh, sorry, duty range. Duty range is 1024. Multiplied by duty percentage, that's 25%, and then divided by 100. That gives us 256. So what this is going to do is this is going to pass in the 256 value over to set duty HW. And that is over, where is it? Here. So it's gonna pass in, it's gonna pass that value in here, and this is where the this is the actual duty value. So technically, if I know um what the resolution is, which obviously I should know because I'm the one, creating it. If we know what the resolution is, then based on the duty percentage that we want, we can pass in a specific duty HW value. Okay, this is great. This is great. I hold on. If I so we have a frequency, right? And we are setting a duty percentage. This is a duty percentage. This is a duty percentage. Now, what I've done here is I've set a duty percentage of duty percentage sounds so funny to say, or maybe it's just the way that I'm saying it. Anyways, I've set a duty percentage of 10%, right? Let's say I want to change this. We have a 20-bit. I think that would be a problem. If I try to take this down, that would be a problem. Um, I don't know what our max, what our resolution should be, because okay, one of the things that I learned as I was exploring this entire thing, this like how all of the math surrounding this works, is that you have a couple of variables that you need to. What is? Sorry, I keep um because I'm using NeoVim, so I keep forgetting that I have to hit the escape key to exit out of insert mode. Okay. Yeah. Throughout this, I've learned that, or throughout trying to solve this problem, I've learned. Actually, I need to note something down. Okay. I'll look at this later on. Okay. So what was I saying? Yeah. Throughout trying to learn, throughout trying to understand why my code wasn't working, why the LED would fail to blink, given various values that I was passing into the PWM functions. I learned that okay, so we have a couple of different variables at play here. We have our PWM. I should turn off the spell check. Yeah, we have our PWM um, frequency, right? We have our source clock frequency. So actually, that's just APB clock. We have our clock divider. So we'll say clock div, and we have our res bits. Okay. Now we cannot change the APB clock. I mean, for the sake of this example, let's say we cannot change the APB clock. I'm also glad that I'm on this page here. I just realized that because I'm looking at this on different screens. So um, throughout, 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 where? No, hold on. We cannot. Sorry, I don't know where throughout came from. But yeah, we cannot change. Let's for the sake of this example, we're going to say that we cannot change the APB clock. Okay, or rather, I mean, APB clock would be 80 megahertz. Let's say for the sake of this example, we cannot change what the clock source is going to be. So let's just call it a constant 80 megahertz. Let's for the sake of simplicity. I actually don't know if we can change it or not because I haven't seen options to change it. So I'll have to see like what's the right way to go about that. But yeah, for the sake of this for the sake of this example, let's say it's 80 megahertz. That's all we are able to do. Okay. Um, we get to decide our PWM frequency. We get to decide the clock div. We don't get to decide, sorry, we don't get to decide the clock div. We get to decide the PWM frequency and the res bits. Res bits is the resolution of each duty cycle, each period. So that's essentially the number of ticks that each period is supposed to have. That's the number of ticks that the counter is going to count up to in order to, you know, complete one full cycle, one full like on-off cycle. And it's within these ticks that our PWM hardware is going to decide that, hey, uh, after so and so number of ticks, we turn the signal off for the remaining number of ticks. Okay, back to this. So we get to decide our PWM frequency. We get to decide our resolution bits, right? Depending on what we decide these two values are going to be, either the HAL or the ESP32 hardware, one of these two. I'm not sure which one it is, so I don't want to give out wrong information. Either the HAL or the ESP32 itself is going to calculate a clock divider. The clock divider is what's going to be responsible for dividing our APB clock appropriately to get, you know, whatever counter values and how many ever ticks we're supposed to get. The clock divider decides that. Here's the thing though, we have a limitation with the clock divider. The clock divider is an 18-bit register. However, only 10 bits out of those 18 bits are the integer portion. And that's like your maximum value is kind of dictated by that, because only 10 bits out of that only 10 bits out of those 18 bits is the integer portion. So 10 bits is 1024. So you only get between, you know, 0 and 1023 in that register. Even though it's an 18-bit register, you only get 10 bits. So your well, okay, you as in the integer portion, you only have, in terms of max value, you only get 10 bits. So you cannot go further from that. If you try to go further from that, it throws an error and things break and things don't work. That's why our code wasn't working previously, because I don't remember if I went over this yesterday, because we did do calculations up here. I remember, um, let's look at this calculation, for example. Initially, I had set I was trying out like smaller duty resolutions. I was trying smaller bit values. So I tried to go for 5-bit duty resolution. Okay, 5 bits would be, just ignore that number for the time being. 5 bits would be 32. So each period, according to a 5-bit resolution, each period can only have 32 ticks in it. Sorry, no, yeah, correct. Sorry. So according to this resolution, each period can only have 32 bits in it. Given that, given that, given this formula, if we try to calculate the clock divider for, let's say, 5 hertz, our clock divider comes up to 500,000, and we only get 10 bits, which is 1024 for the fractional divider. So this is why we were getting an error. So when we are doing our calculation, we need to consider the limitation of the fractional divider, which we cannot set, but it gets set based on the FPWM, as in the PWM frequency that we want, which in this case is 5, and the duty resolution that we have set, which in this case is, right now it's 5. 32. Yeah. So five bits, so a maximum of 32. So in order to make this work, we need to either increase the frequency or increase the number of bits that we are providing. So if we take this up to, let's try 10. That is still high. Let's try 15. That's better. So that fits within 1024. So in order to make this 5 hertz frequency work, we need to give the resolution, we need to give our counter a high enough resolution that the clock divider doesn't end up going more than 10 bits in size. Learning this has changed things for me. Holy shit. I am so glad that I took the time to dive deep into the hardware, like even the high speed and low speed channels and stuff like that. I'm so glad that I took the time to dive into this. And I think further on, I'm going to continue doing exactly that. Because we do have like the MCPWM coming up next. We haven't done too much with MCPWM. Oh, holy shit, dude. Okay, now that sorry, I'm really excited about this. Um, now that so we have our fading LED example. Our fading LED example, now we can do the fade. Oh, the next thing we need to do is learn about fading. Yeah, okay, okay. The next thing we need to do is learn about fading. Because so far we've done the bare bones PWM. Actually, this reminds me about the question that I had to ask Gemini. Give me a second. Let me copy this entire block. Dude, I love NeoVim. Holy shit. My God, dude. NeoVim is amazing. Okay, I'm gonna copy. Let's do a wrap here so I can copy this entire thing. Oh, there. Much better. So we'll yank this and then I'm going to paste it here. Okay, I'm learning about the ESP32 using no STD Rust um, with ESP HAL. Help me. What was I trying to understand here? Oh, yeah. Um, read the following code and now answer me and now clear a doubt of mine. I'm assuming, wait, am I right to assume that as soon as the channels configure method is called, the channel and therefore the pin starts outputting a PWM, a constant PWM signal? If so, doesn't this mean that it's just gonna keep outputting the entire time? How do I turn this on or off? Does this consume a considerable amount of power, or can I just let this keep running? Because I remember so this comes back to the concept of like how you can turn the CPU off or put the CPU to sleep after you have configured your PWM hardware to do stuff. It's just going to keep doing stuff, right? You can turn the CPU off or put the CPU to sleep or whatever, and the PWM hardware will keep running independently. but I haven't seen people talking about like turning the PWM hardware off. Also, what happens prior to configuring channel? Is it still outputting stuff? Yeah, I haven't thought about that. Like, where's the quote unquote on switch for this? Okay, so Gemini replied saying, you've hit on a core aspect of how the ESP32 LEDC or LED control peripheral works. Your intuition is spot on. The LED is a set and forget hardware peripheral. That'll be good to remember. Once configured, it operates independently of the CPU. Does it start outputting immediately? Yes. As soon as .configure is called on the channel and it is linked to a running timer, the hardware begins generating the PWM waveform on the specified pin, GPIO12 in your case. Okay, because the LEDC peripheral is implemented in hardware logic, it doesn't need the CPU to quote unquote bit bang the signal. I think bit banging is a software implementation of PWM, if I remember right. Yeah, I haven't touched that so far. For now, let's stick to the hardware side of things. Okay. It will continue to oscillate at 2 hertz. That's because I've set 2 hertz with a 10% duty cycle until you explicitly tell it to stop or the chip is reset. So in our case, resetting would, oh, it is running just by itself. I was about to do a control R to, reset the chip to show you the chip resetting. It does reset. It does reset. Anyways, you know what? Okay, I could do that right now while I'm maybe I could change this to 3 and I've set the duty resolution to be 10. Instead, oh, yeah, this would have thrown an error. Actually, I could set the duty here, right? So I could set it to 50. What did I set I set it to 3. So we should be looking at 3 blinks per second. Yeah, okay. And to reset, there. So you can see it stops for like a second and then it starts. And you can also see the output each time I reboot. Okay, all right, cool. By the way, dude, I I kind of want to rewatch Reboot. Reboot was um one of my favorite cartoons growing up. Like holy shit, dude. I feel like that specific cartoon, that specific series, it really like massively expanded my interest in computers because of the way things were shown in it. Holy shit, dude. Anyways, okay, back to this. So how do I turn it on or off? In the no STD ESP HAL environment, you have a few ways to manage the output. Change the duty cycle. The most common way to turn off, quote unquote, turn off a PWM signal is to set the duty cycle to 0. This says that it is effectively off. Okay, all right. I could do something here. I could wire this to. So far, I don't think we've had examples of button presses. Have we had any examples of button presses like throughout this entire thing? I don't think we've had examples of button presses. I think button presses come in. They probably come in somewhere here because there's a thing where like you have to read the input. I think I should also cover embassy before we go into button presses because um, as we start doing more and more things, we are going to need to make things async. Otherwise, the timing is going to be very off. And a bunch of things are going to end up getting delayed, happening late because the previous thing was waiting to finish. Like, for example, start duty fade. That waits for the entirety of one fade to finish before it moves on to the next fade. As in, if you have two LEDs and they both have to fade, then one is going to fade first and its entire while loop thing is going to finish. Then the next one is going to fade. So we need to find a way to, have both of them running independently. Wait, actually, what would happen if oh, okay, okay. So I was for a second there I was wondering like, okay, because if we come back here and we look at this code, let me uncomment this. This is our loop code, and in here this is basically just looping from 0 to 100. Sorry, fading from 0 to 100. But in order to make that fade happen, we have to run this while loop so that while the fade is running, nothing else happens. It doesn't progress further. So the result of this is that it it fades from actually, how is this going to work if I have a very low frequency? I'm curious about that. No, I'm actually really curious about that. Hold on. How is this going to work if we have an error? Hold on. Is that the only one? Okay, that's the only one. Okay. Uh Yeah, I'm curious about this. How would this be working? Because the whole idea with fading with PWM is that PWM is creating an illusion by um by blinking the LED fast enough. Okay, yeah, that's our yep. Let's let's look at that again. Yeah. Oh, there's something interesting here. Um, Let me re-upload that. So for the illusion to work, it has to be a high enough frequency. And I'm assuming what it oh, back up, back up, back up. Wait, wait, wait. Um Fade, start duty fade. Do we have access to the other function? So we have a bunch of these functions here, right? We have set duty, configure hardware, or configure HW, start duty fade HW, try into start duty fade, um, configure with drive mode, is duty fade running, into configure, is duty fade running, set duty HW, and so on. Okay, we don't have access to set duty without fade. So we need to, I mean, set duty without fade is this, isn't it? Yeah, okay. So with start duty fade, we are specifying a, a duty percentage, a start duty percentage, and an end duty percentage. And what this function is going to do, I'm assuming, is it's going to stretch out, it's going to change our duty percentage over over the course of the duration that we have set. And because it's changing, and this is where the blinking comes in. So we can get rid of this and this. um we can set I'm curious about this. If I set the duty percentage, sorry, the resolution duty, because here we have set it to 5 bits, and that works because this is a 24 kilohertz PWM frequency, right? But here we have 20 bits. So I'm curious about what the divider is going to look like there. It's supposed to be APB clock divided by, I need to remember this formula, and this one specific formula, I don't think it's mentioned in here. However, they did also mention calculating the highest resolution. I think they mentioned actually both highest resolution and lowest as well. The division factor, yeah, there you go. Yeah, the lowest resolution is calculated when the clock divisor is at its maximum value. And here they're calculating the lowest resolution. I also learned, by the way, division and multiplication are used for setting and getting, I think, the lowest bits. No, what was it? There was because like in the 10-bit register, or sorry, in the 18-bit register, in the, yeah, 18-bit register, we only get 10 bits of integer values, right? 10 bits for storing integers. Um, in order to set that value, you would have to I think multiply or divide by 256. And the reason for that is that 8 bits is 256, and you are trying to set the value for the higher. So I think it's bit shifting. Yeah, I think it's for bit shifting. I don't remember, dude. Is it for bit shifting? Let's do 0. Um, okay, so let's do an 8-bit value. 0. Okay, that's 240. Okay. Now let's say, how would I read? Okay, let's say we have two. So let's do bin 255. Oh shit. Um, bin 16. Okay, sorry, bin 15. So that's our 4 bits. So if I do 16, I want to see if this fills out all of the bits. So if I do 16 multiplied, that would be too big. So we have 16. What was there was a certain sorry, I'm not able to remember this. Wait, I need to ask Gemini. I need to like refresh my knowledge of this. Hey, I had recently had a conversation with you about um, multiplication and division being used to set or get bits in a register. I can't remember what it was. Remind me. It's a classic moment in programming, using math to do what we usually leave to bitwise operators like AND or bit shift. The logic boils down to the fact that every bit in a binary register represents a power of 2. Because of this, multiplying or dividing by a power of 2 is functionally identical to shifting bits left or right. Here's a breakdown of how we used math to mimic bit manipulation. Setting a bit. In bitwise logic, you use so-and-so to create a mask. Okay. The math, if you want to set the third bit starting from 0, you multiply your value by 2 to the power 3, which is 8. You multiply your value. Okay, okay. Wait, what does this say? If you want to set the third bit starting from 0, okay, so we're going to say 5 multiplied by 2 to the power 8, okay, and then bin that. Setting the third bit starting from there. Wait, 2 to the power 8. You multiply your value by 2 to the power 8. Oh, you multiply your value by 2 to the power 8. Sorry, you multiply your value by 2 to the power 3, which is 8. Okay, okay. All right. In binary, this moves 1, 0, 1, 8 places to the left. Dude, okay. I'm gonna revisit this whole thing and then I'll explain it like in the next stream because I was trying to explain it, but I couldn't remember what the logic was. Basically, there was logic where you could multiply or divide to specific set specific bits in the register, instead of having to do a bit shift operation or bit masking or stuff like that, which kind of it would be bit masking. I'm not sure. I don't remember. Okay, all right. I'll look into that off stream and then I'll talk about it in the next stream. What was I gonna do here? I was gonna calculate. Yeah, I was curious about this. 20 bits, okay, and 5 hertz frequency. If we crank this up to 5 kilohertz instead, wrong place, kilohertz instead, uh, will we still be good? 20, okay, 5,000. Okay, okay, okay. Wait, wait. Um, 20. How is this gonna work? Is this gonna work? Let's yeah, let's try this. Wait, did it did it work? It did not work. Yep, it did not work. There's a problem. So this is a 20-bit. How do we calculate what the resolution is going to be? There's, I think, res bits, log 2, so and so. We have our divider, right? We have our divider, so we can calculate it like that. We're going to say math.log2 APB clock divided by 5,000 multiplied by, what was the value? 0 0.015258789. Uh, there. I think that's our resolution. Res bits is 20, but it doesn't seem to be working. Okay, okay. We've set that for HS timer. HS timer is here. Oh, oh, it is oh, wait, no. HS timer is so HS timer is down here, and that's for the red LED. I keep forgetting that. 20 bits, 5 kilohertz. Okay, all right. I am curious about this. So we're going to try setting it to 50. And I want to see if the LED becomes at least, kind of lit up, because I'm not sure if it is actually doing the fade or if it's just running the PWM signal the entire time. Okay, it's not running. So what could be going on here? Because there does seem to be an issue here. Let me feed this into. Actually, I have the other conversation open with Gemini here, right? Okay. I'm doing ESP32 development with no STD Rust using ESP-HAL. Here is my code, and I need to modify this a little bit. So let's say 50%, and we're going to do... Actually, one last thing I need to check. Let me do this, okay? And then we're going to upload this. And in the meantime, I'll ask Gemini the question. So 20-bit duty resolution, uh, kilohertz, 5 kilohertz. Okay. Is there a reason why my LED is just off? It looks like you've hit a classic gotcha in the LEDC peripheral logic for the ESP32. While your configuration looks syntactically correct for the ESP-HAL, there are two likely culprits, one hardware specific and one logic specific. The 20-bit duty cycle trap. Okay. The most likely reason your LED appears off is the combination of 20-bit resolution and 50-bit duty cycle calculation. In the ESP32 LEDC peripheral, the timer's bit depth determines the maximum value of the duty cycle. When you set duty so-and-so 20-bit, the maximum duty value is 1 million so-and-so so. Okay. What did hold on. What did I calculate here? I calculated res bits. I didn't calculate the maximum. Oh shit, I made a mistake here, dude. I made a mistake here. Let me do something real quick. Okay, let's take this down to 1K. Oh, actually, we could feed it in here. That's a bad idea. Let's take it up to 10K. That makes it 19. So I'm going to try one more thing here. Okay, yeah, still not working. All right, okay, so we've got a new problem that we need to solve. All right, continuing reading this. The maximum duty value is 2 to the power so and so. The issue, many versions of the HAL or specific chip revisions have constraints on the maximum frequency achievable at high bit depths. The math at 5 kilohertz with a 20-bit resolution, the required clock. Dude, this is kind of embarrassing because like I did this calculation earlier, um, this one, and I read the number 20 and I thought it was 20 ticks. So I thought that was the essentially the duty resolution, whereas what we were calculating here was res bits. So that was the number of bits for the resolution. So if we round this off, it basically becomes this. Um, yeah, yeah. Anyways, okay, the math at so and so, okay, the required clock speed might exceed what the APB clock can provide after the internal prescaler is applied. If the calculation results in a divider less than 1, it did. Okay, the hardware often defaults to a state where the output remains low. Try this first. Lower your resolution to 10-bit or 13-bit. For an LED, you won't notice the difference in smoothness, but it's much safer for the hardware clock dividers. Okay, let's try that. I actually didn't think about that. Or maybe I just wanted to see like how, because like at a much higher resolution, they do say though that, oh, they do say that as you increase the frequency, you have to reduce the resolution. I did not take that into account. So far, we've only been looking at the low end. Oh, shit. Accidentally hit my other keyboard. Yeah. So far, we've only been looking at the low end of the frequency. We haven't played around. Holy shit. We haven't played around with the high end of the frequency. Yeah, I mean, as you increase the frequency, you have to reduce the resolution. I don't think I understood why you have to do that though, but I did understand that as you increase the frequency, the resolution has to increase. Sorry, has to decrease in order to fit all of the ticks that are required. Though, would that be actually, yeah, that would be a constraint, wouldn't it? Because the counter has a limit. The counter register. Sorry, give me a second. Okay, yeah, the counter register has a limit for the number of values that it can set. Now, how do I calculate this? How do I get the number of ticks that um, we need for a given resolution and given uh, frequency? How are we calculating this? Would it just be multiplication? Oh yeah. Wait. Frequency is number of cycles per second, right? Duty resolution is the resolution. It's the number of ticks per cycle. So yeah, we just multiply it then. So I think the reason why this is not working is because if we are doing 20 bits and then we multiply that by 5,000, did I say 20 bits? No. Yeah, well, 20 bits, but this, that is our value. And that is significantly more than what the counter register can back up. No, that's wrong. That's the total. That should not be an issue. That is wrong. No, sorry. That's wrong. I was trying to figure out if this is the problem and this is not the problem. Because this is the total number of ticks that we're gonna have. Each time the counter is counting, it's counting for one period. It's not counting for, the entire um second. Yeah, no. There's something else going on here. I'm gonna continue doing research on this. Um, yeah, I'm gonna continue doing research on this. I unfortunately do have to end right now. Give me a second. Uh, just a second. Oh, holy shit, dude. I've been quiet for a while. Sorry, I'm just looking through the list of people and I'm looking for somebody to raid and yeah. Okay, let's see if I'm able to. Nope, can't go there. Um, oh wait, somebody here is building circuits. At least that's what their thing says. All right, so I'm gonna set up a raid. Okay, all right. So we're gonna go to this person's stream. Um, yeah, that's gonna be it for today's stream. Uh, back up, back up. Did I click on? Okay, they were building circuits, and then now they're drawing. That's fine. Okay, cool. Um, but yeah, we're gonna be rating this person, and that's gonna be it for today's stream. We made some decent progress today, and I'm gonna continue doing research on this off stream as well, because I want to get down to you know, the reason why this is. I want to narrow down the reason why this is happening. I just need to sit and think about this for a while, and also talk to Gemini about it. But yeah, I'll get there eventually, and I'm gonna continue doing my other research, cyber deck related stuff, and all that. Yeah. Good progress today. Amazing progress today, actually. I'm pretty excited to continue moving forward with this. We are making a lot of good progress now. I'm happy about that. Okay, that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.